Well, welcome everybody to the Co-Solving with ANSYS CFD webinar. This is actually the first time this webinar has been given, so it's kind of exciting to introduce new capabilities. And we'll be talking about how this is actually just a good start, and there's even more capabilities coming online soon. But for right now, this opening graphic is pretty useful because it shows kind of the concept of a TD model and a ANSYS Fluent model co-solving and working together to produce a combined answer set with the wall temperatures here on the outside of this barrel being the same in Fluent as they are in Thermal Desktop. I'll be talking more about this example later, or at least this demonstration case, along with some other examples, but just not often we pause at the opening slide here and let you see the concept in one slide. The agenda for today is to talk about what we have available now, and by now I mean Thermal Desktop 6.2 and ANSYS 21R1. You need to at least have those two for these features to work. And I'll also be then talking about future progress here, that the work that's currently going on that will be released in 6 to 12 months, and then even more later, since, like I say, this is the beginning of new capability rather than just something that's been introduced over and over again. Going to be talking about explaining the strengths of each application, basically why we're doing this, and then talking about ANSYS System Coupling to answer the question of how we're doing this. And we'll go into details of how you set up this kind of problem. Maybe more details than you want to know if you're just perusing to see what's possible. But I think you'll get a sense of how easy or difficult this is, and the answer is pretty easy to get something going between the two codes. And then talk briefly about the examples that are available. You want to make sure you have grabbed the handouts, the PDF in the handout section, because it has some links to these examples. And those are ones that I think are basically the documentation for this capability is best taught by some simple examples, and you'll get the idea. If you're watching this video later and are not attending the webinar, you should be able to find that through support. So in terms of the strengths of each code, why you do a co-simulation, we've got some fairly complex applications targeted here. For example, cryogenic tanks beyond what a FlowCAD compartment could do, or aero heating beyond what we do with the Thermal Desktop BC Mapper. Another case might be regenerative cooling of combustion chambers and nozzles, where you can do the shell and the cooling chambers and so forth, and TD FlowCAD, but then you might want to use CFD for some of the complexities of what's going on inside a chamber itself. This fourth application is kind of interesting. It's very common to have a model of a vehicle already built inside of Thermal Desktop and already validated for thermal vac conditions. But then you need to also analyze it during a period of ground cooling, ground equipment cooling, where you're blowing dry GN2 through the system. So that would be a case where maybe you'd superimpose CFD onto a TD model and see the obvious combination is not necessarily just the strengths of each application, but just more the time history of how the models came to exist. You'll probably be hearing a lot more about comfort in the coming years as we become more and more focused at launching humans at the moon and Mars. But that also would apply to airplanes and ground vehicles too. Turbo machinery, another active area of interest. We do a lot at the cycle level, in which we treat the turbo machines as kind of black boxes, but a lot of times you want to dig deeper inside the component more than just secondary flow analyses, which we do a lot, but also maybe looking at mean line simulations using CFD. A very common thing we get asked are valve system interactions, so I'll give an example of that later, so I'll talk about that right now. Another interesting application is custom heat exchangers, where you're not going to find the answer of what your heat exchanger should look like in the back of a book. Hopefully you're aware of the unique strengths of the TD suite. the ability to work at system or vehicle level and work in transients too, over multiple mission scenarios. So we're talking about zoomed out, fast simulations at a large scale, and the ability to do even multiple scenarios would be something you would look at for bracketing or what ifs or statistical design. We of course do with RadCAD fast radiation solutions with orbital environments, somewhat unique, and also somewhat unique is the ability to do 1D flow network solutions with FlowCAD that can be complex, two-phase, transient, and so forth. But definitely things you would not want to do in a CFD analysis. But of course, the strengths of each application, the weaknesses, TD Suite does not include a CFD solver until we connect to a CFD solution. So of course that's the primary motive here, is to be able to fill that gap for folks who want to do CFD analysis without completely changing over or trying to analyze something they can't, through a CD solver. So that's the question of why are we doing this? I'd like to show a demonstration of that by going back to a kegerator example. That was what was shown on the first page here. A kegerator is basically a keg inside of a small refrigerator. This work was presented at TFAS last year, so I'm not going to go into gory details. And it's actually a very complex problem. As you'll see, we do things like use natural convection with ANSYS and add a bunch of other components in there. And so it's kind of more than you'd really want for a sample problem. So it's more of a demonstration case, but we used it because it should be reminiscent of applications that you're used to. A tank that's being pressurized and drained and so forth with temperature gradients should be something a lot of you can relate to. We're using ANSYS for the natural convection because, of course, the kind of complex natural convection inside cavities like this is something that we don't have built-in correlations for. And so it's even a little bit of a stretch to use CFD on this, though, because if you've worked with natural convection, you know that it can easily be unsteady even in steady boundary conditions. And then if you try to do the 7 to 10 day long transients that we're doing here for cooling down a kegerator, that's really pushing it for a CFD capability. And so you probably end up using, more realistically, using CFD to create correlation basis for a TD model. So you can then run CFD, get a correlated model, and then run TD only after that for analyzing days and weeks long events. Or you might do long intervals with steady CFD, and I'll talk about that in a minute. So if you go through the strict idea of I'm going to do transient CFD and transient thermal desktop and then go for 10 days of real-time simulation, you're probably not going to get there. The thermal desktop RadCAD side of this is, of course, the walls of the kegerator, the walls of the keg and of the fridge, and all those kind of workings are very easy to do in TD FlowCAD. Of course, we're actually using TD Direct because it's a fairly complex geometric situation with mesh. We even went so far as to add holes in the handles and the curved rims so you don't cut your hands. All of that's maybe a little bit excessive, but we can do that, so we did. RadCAD internal radiation for all the radiation both inside the keg but also in between the keg and the walls. And then just to make it more interesting, we added in a FlowCAD transcritical CO2 refrigeration cycle, which is definitely not something you're going to find in a home fridge. So this may have been showing off just a little bit, but the idea is it's definitely something you would not try to do in a CFD code. It's the kind of thing FlowCAD does really, really well. So if you did have to add in your refrigeration cycle for the they're not shown here, but for the evaporators up at the top, then that's how it would look. Of course, in a transcritical cycle, it's not an evaporator. And then we use compartments for the insides of the keg, the beer, and not seen here behind the keg is a CO2 bottle. It's also a compartment. It starts supercritical, but then is the 7 to 10 days or whatever it is goes by, and you're pressurizing the keg and carbonating the beer, then it goes subcritical at some point. And then just to have even more fun, we include the dissolution of the gas of the CO2 into the beer, modeled as water, and then we pretend at the end of the 10 days that you're ready for a party, and you tap the keg and put in a spigot, and there's a dip tube down here that isn't shown, and then you drain your keg. And of course, towards the end of that transient, interesting things happen, like when the keg's nearly empty, the gas in the spigot starts to come out of solution and foam up, so that makes it exciting too. So again, the idea is not the specifics, it's just that some of these things are really, really well done by TD FlowCAD. Some of these things are really, really well done by Fluent, and so we want to use the best of both worlds in a combined problem. Briefly mentioned there's even a model of frost growth in the evaporator that's available, but we didn't really, it's really not related to the rest of it. That you'd only get significant frost growth if you kept opening up the door to check your beer, I guess, during the cool down. So this is a model or a demonstration video of that solution happening. It's moving towards steady states. You're seeing kind of the complex flow patterns of natural convection. Replay that again, forming and being displayed on the wall here. And this is, of course, a TD model being influenced by the CFD produced natural convection inside that container. So the idea behind all this is that I want to be able to name one or more TD surfaces and then say they are dynamic boundary conditions to a Fluent CFD run. That's the key, is that there's surface connections between the two codes. You define that from this surface, that surface, they're shared by the two codes, and we're exchanging energy across that frontier. If you do have CFD predictions that really don't depend on surface fluxes or temperatures, then you really can run them in separated mode and use the BC mapper, the boundary condition mapper in TD. But there are a lot of cases, including that kegerator, or any other natural convection for that matter, where a co-solution is required because the thermal response of the wall influences the CFD flow field. And that may not even influence the flow field, but just the energy field, the temperature of the fluid, such that the temperatures downstream of some wall elements are influenced by what's upstream. So that would also require a co-solution. And I'll give you an example of that in a minute. Of course, the TD solution is really very fast. And so that allows you to make a TD FlowCAD model, radiation and so forth, that is fairly complex to surround. So I guess in some ways you can think about it as an incredibly complex boundary condition for your CFD model. But I guess I'd prefer to think of it as a thermal desktop model that's been augmented with CFD. Of course, the example might be external flow over a vehicle, but quite often the temperatures of the surface don't influence the flow field except at very high velocities or special surfaces. So often that's good enough for the boundary condition mapper. But if you do have a case where that's not true, something downstream that's being affected or the flow field itself is being affected, then you'd want to co-solve. Probably a lot more common is an internal flow. Natural or forced convection, mostly because what happens downstream, depends on what happened upstream, unlike an external flow field. And so in that case, like the kegerator example, you would want to co-solve. So that answers a little bit of the question of what we're up to and why we did it. How we did it is basically can give most of the thanks to ANSYS System Coupling. This is a tool that you may or may not be familiar with. If you are an ANSYS user, you probably have heard about it, but may not have used it yet. That's kind of the status it is for most folks. I believe that this started as an internal tool within ANSYS, a way of making different ANSYS products speak to each other. And an example would be structural and CFD, so you could do fluid structures interactions, FSI. But they opened it up and made it available to third parties such as CRTech, so that we can participate in that environment too. Very kind of them. And so we become one of the participants in a system coupling analysis. So system coupling could link Fluent, CFX, mechanical, and so forth here, whereas the CRTech products of TD Direct, Fluent, and Thermal Desktop are linked here. And then we were able to communicate back and forth through there. So some of the features of system coupling is that it can run in steady state transient or pseudo transient. And by that, I mean transient means both Thermal Desktop and Fluent operating in transient mode, maybe both of them operating in steady state mode. Pseudo transient means that one of them is in steady while the other is in transient, which, as you might imagine, is very convenient, especially running maybe steady CFD with transient Thermal Desktop. You still have to communicate every now and then because if the flow field weren't influenced by the temperature, it wouldn't be a useful co-simulation, but it is quite a good convenience to be able to throw away the time dependency on one side but not the other. How we couple these together is by a fairly standard method. It's hard to explain, but it's a simple idea of on one side of the interface, specifically on the Fluent side, it's a convection coefficient and a near wall temperature. So this is not the wall temperature itself, it's stood off from the wall a little bit. And then Fluent supplies the wall temperature, and this allows the two programs to iterate back and forth very efficiently, and especially in steady states come to a convergence stably and with few iterations. System coupling does have a few options here, including, for example, when you're trying to make a Fluent model speak to a Thermal Desktop model, maybe they don't line up perfectly. And so you do have the ability to do transformations of coordinates and so forth of models to make them line up. It's generally true these days that most Fluent users are starting with space claim these days. I know that wasn't true in the past, but more and more I think that's becoming true. And the good news is, of course, we also use space claim for TD Direct. So that provides a nice common basis that if you're starting from the same TD Direct model, you don't have to worry about this kind of thing, but you do have the ability to come from different sources too. The other options you have are things like setting convergence criteria, what's the end time and the coupling interval. Not the same thing as a time step, it's more when do the two codes stop and communicate with each other and update their temperatures and references and so forth. Then some other advanced parameters for controlling this interface and that coupling. There's also pulse processing and debug tools, tools for handling distributed processing, restarts, and you generally work, in the past it's been mostly command line, but they're moving more and more towards GUI, as are we. So we'll talk about that in a minute. I want to mention the meshes because, as you can see here on the left, a Fluent mesh doesn't look anything like a TD mesh of the same system. Of course, we don't bother meshing the fluid volume itself because we don't do CFD, but they do here. But the structure, you can see it's a hex surface grid here for the wall here, which doesn't exist in Thermal Desktop. And over here, you can see there's we're using tri-elements and they're curved. So curved elements, of course, don't exist in ANSYS. So that doesn't matter. We can use disparate meshes as long as they map to each other, as long as geometrically they coincide with each other. So this little curved handle here that you see for the keg, there should be a curved handle over here if we're going to have those communicate with each other. And if I were to move this keg over a couple inches, they would no longer be coincident. So I have to be careful to make sure that it's the same dimensions and location and features and so forth if I'm going to do a co-simulation. Otherwise, the mapping will miss. But system coupling otherwise doesn't require the meshes to be conformal. So it's going to handle that mapping for you quite nicely. Inside of Fluent, I'm sorry for how small this graphic is, but inside of Fluent, it's pretty easy to say, well, I want this coil to be modeled in Thermal Desktop. And so the outside of the coil is to my CFD model defined by a boundary condition coil surface. And inside of coil surface's thermal tab, you have the traditional options of heat flux or temperature, convection, and so forth. But this down near the bottom here, you'll see via system coupling. And that's the key. You say this is going to be kind of a live boundary condition. It's going to be handled by a connection to another code. And that's about as much as the model has to be mutated to make it work in this environment. And now when the system is running Fluent, we'll be providing the connections to the outside of this coil. So what steps do you do? You should start by creating a new working directory. You do have to be a little bit organized here because otherwise you've got a lot of files and a lot of things that could communicating with each other that need to find each other. So it's best to just start with a new file for a co-solution. Inside of that file, you'll place a file called run.py, which is a Python script file. You don't worry, you don't have to speak Python, but you do have to be able to look in that file and maybe change things like what are the convergence criteria, time intervals, locations of files, and things like that, so that it can find the models and where you put them. You will want to place a thermal desktop model in one subdirectory and place the Fluent model in another subdirectory and all its data. So kind of keep them all separate, but then you're going to point to those locations in your script file. Inside of Thermal Desktop, any surface you want to be available for a CFD coupling, you call coupling region. And this is case specific. However, the surfaces don't have to be contiguous. So whatever you call coupling region, wherever it is, will participate in the CFD link. So this is the equivalent of that via system coupling I showed you on the last page. There's also a file you need to create, the system coupling file that says, simple things like, do you want TD to run in steady or transient mode here? You're really declaring to system coupling whether your TD model has been set up for steady or transient. And the only other thing you have to do is, in whatever case you want to link to CFD, you need to call OpenSF in operations. And this creates the link to Fluent. So that when you're finally solving, it's actually Fluent and Fluent, sorry for the name collision there, that are speaking to each other during the coupling. And of course, you might have a bunch of other cases that have nothing to do with the link, for setup, verification, calibration, or whatever. But the cases that are linked, you need to make sure that that's added to your operation sequence. And as I showed you in the previous slide, all you do is in Fluent is say via system coupling for whatever surfaces are parallel to these, or correspond to them, I guess is a better word. So coupling region as a domain inside Thermal Desktop corresponds inside Fluent to via system coupling. And once those two things are set, they know to speak to each other, and hopefully they're geometrically overlaying so that they will map. Within Fluent, you can have it write out the equivalent of this CRTech system coupling file, and then you need to make sure that the run script points to that file. So basically, this script needs to know where these two files are, and these two files say where my runs are. And then there's a batch file that you can run to launch the whole run once you've set this up. You do have to have Fluent initially closed, by the way. And it's I'll show you what these files look like, but don't be too worried. I don't speak Python. I can edit a file. And we are moving, and ANSYS is moving also away from files and scripts and so forth and into GUIs more and more. But right now, you do have to place a couple of files and edit a couple of lines. So an example of the working directories, this would be a working directory called heating coil. And inside there, I've got a folder called CRTech that contains all my thermal desktop models, my output files, my run directories, anything you want that has to do with that model. You create another folder called Fluent, or whatever you want to call it, but that folder is now going to be where all your Fluent model and restart data and so forth like that is contained. And then this Python script, you have to do things like just point to, hey, where does that SCP file live in the Fluent directory? Where does it live in the CRTech directory? And then those files, point to the run to be made. It also contains things like, hey, I'd like to run this thermal desktop drawing in this case. So it can get specific. You might have multiple cases, multiple drawings, but this is the one that this script will run when you're running system coupling. This folder is created by system coupling when it runs, so that's your essentially coupled output data is there, and this is the file you use to run it. And like I say, if you're a little bit worried about editing a text file that looks strange to you, it's just a couple of simple places you need to find and change, and they are moving. Both ANSYS and CRTech are moving more and more as this thing gets mature into GUIs instead of file editing. So when you're running system coupling, it looks like this. As each iteration happens, it'll show you what the metrics are and how each side is working. One is called the Fluent, is showing converged here. The CRTech solver is showing converged here. It took the CRTech solver 20 seconds or something to run. It took the CFD run about 700 seconds or something to run. And so, of course, they're speaking back and forth, but it only took, in this particular case, a few iterations to converge. That's, of course, greatly accelerated by having started by previous solutions, but both codes are pretty good about that. You don't really need to know how the sausage is being made, but it's helpful sometimes to know that system coupling, when it launches Fluent, and it doesn't actually launch TD or Fluent or anything directly. It launches a thing called the CRTech ANSYS coupler. We'll come up with a better name for that maybe in the future, but right now, this is the thing that communicates between CRTech and the ANSYS tools. That coupler, in turn, launches Thermal Desktop, runs the case. You remember that was defined in that file I just showed you. Sets up all the communication and everything, and then the case, of course, launches Fluent, which now performs the actual coupling. So a little bit of a shell game there, where CRTech launches TD, launches Fluent, but ultimately that was what speaks back to the Fluent run is Fluent. And so that's all kind of hidden from you, but just so you know what's happening when you make a run. So I mentioned that this is best taught by example. So we have two main examples. There is some documentation that's available to you if you would like to read in general terms, but otherwise walking through a couple examples, you'll get the idea. In this example, as you show, is you can at least see in the TD view that this is a shell of a annulus in which water is flowing and a heated coil inside. And it's being solved here with the representation as it appears inside of Fluent and representation inside of Thermal Desktop. And this is the reason why you really need that PDF, or you can type down this link. This is the URL that takes you right to this example with all the documentation. It was adapted from an ANSYS Fluent tutorial because that's an easy way for us to make sure that it's a sensible Fluent model. And in this case, water is flowing from one end to the other. And inside the sample case, we solved this in both steady and transient cases. But before I leave this, I wanted to point out that if you'll notice that each coil is in the wake of the upstream coils. So this is a good example of it's kind of external flow from the coil's perspective, but each coil cares about what's upstream of it. So it needs a co-solution if that coil is not going to be modeled entirely in ANSYS. And of course, there's hopefully some good reason why this coil wouldn't be modeled in ANSYS, such as it's a condenser of a loop heat pipe or something, who knows. Another example is a natural convection cube. And again, we've just borrowed this from an ANSYS tutorial because that's a pretty easy thing to do. Here's the link to the example problem and all the documentation. In simple terms, this is a 25 centimeter cube where the side that's been removed here is actually a boundary condition. It's isothermal temperature set. I think it's about 500 K. So it radiates and all the air inside naturally convects to deposit all the energy. On the inside of the cube, it's got thick insulation, and then it convects and radiates to ambient on the outside of the cube. And so we solved this, of course, both with ANSYS and without ANSYS. And we also solved it with just ANSYS. So This is, again, adapted where we, instead of using ANSYS to solve for the wall temperatures and the convection and radiation and so forth, we use Fluent to just solve the internal natural convection here and then use TD to solve everything else. One interesting thing about this sample problem is that we showed how you can use ANSYS results to kind of correlate to a TD model. So at least for a steady state, it's pretty easy to say, well, I don't want to solve that internal convection in Thermal Desktop, but I don't want to run ANSYS CFD every time I investigate something. So at least to the extent that you can trust your own correlation, you can correlate that data and apply it inside of here, and then solve only in Thermal Desktop to the extent that correlation replacing CFD was a good idea. And that's engineering judgment. And then finally, as shown in this picture here, we're also use this as a validation case just to make sure we're getting the same answers. In other words, if we co-solve with ANSYS and TD, do we get the same answers as when we solve with just ANSYS? And that was also done on the coil sample, but it wasn't discussed very much in that sample problem. So we talked about it a little bit more just to make sure people felt comfortable that, yeah, you're getting the right answers. So that's really all I wanted to cover in what's available right now as of the 6.2 release, which happened about 3 months ago or so. But we are working towards 6.3, as you probably guessed, and there's a lot of stuff in progress right now that you should be seeing soon. So I want to touch on that briefly. One is CFX connections. Fluent kind of connected the system coupling sooner or stronger, I guess, than CFX has, but CFX should be coming along pretty soon. So if you're a big fan of CFX and not Fluent, then you can hope that CFX will be available soon. And as soon as it's available, it'll just be plug and play. You won't have to have a new version of Thermal Desktop or anything. It'll be through system coupling that the connection appears. Excuse me. Another thing we're trying to do is we understand that right now a single coupling region, even if it's not contiguous, is not going to be what people will want to do forever. So trying to provide a little more capability to customize multiple zones with distinct properties, distinct controls, methods, and so forth. So you can handle more complex problems. I mentioned that we were using the convection coefficient reference temperature connection method because that's a nice, fast, safe way to go. But an alternative is to do a little bit more traditional, seemingly simple approach of flux on one side and temperature on the other side of the connection, which is great for energy conservation, but unfortunately isn't great for long time steps and fast, safe convergence. And you definitely don't want to be taking too many coupling intervals or too many iterations when you're running a CFD code. So we're working on improved methods for that to be able to basically faster convergence, longer transient coupling intervals, basically less hesitation to use this kind of feature. And as I mentioned more, moving towards GUIs instead of editing files. This is actually unrelated to the CFD work I've been presenting, but another, being ANSYS partners now, another connection we get that's requested periodically is the ability to use Thermal Desktop to predict temperatures within a thermoelastic load case definition where you're working in the mechanical structural side. And that's often done in Workbench, unlike the CFD runs. So probably working on that too is coming up in the future. Another area of connection that is going to get a lot of attention, we think, is the 1D to 3D flow connection. I think about 2/3 to 3/4 of the people queried wanted to see this even more than they wanted to see the connection I just showed you. So basically, this is CFD meets FlowCAD. And the idea being that CFD has a FlowCAD boundary condition as an inlet. So whatever's flowing into the CFD model is not just constant temperature or velocity or something like that. It's actually a live co-solved some complex system upstream of the CFD volume. And similarly, CFD can have or FlowCAD can have a CFD boundary condition at its inlet, or both. Something where you're running along in FlowCAD, stop, do a CFD run in the middle of the plumbing system, and out comes FlowCAD at the other end of it, ideally. And of course, one of the things we're working towards in that is that valve interactions application that I talked about. And this is just kind of a cartoon example, but this would be what if you had a complex control system, who knows what kind of diaphragms and controllers and actuators and bulbs and all that other stuff you might have there, or flaps. But let's say you had a complex valve here that needed to be solved with CFD for various different dynamics and positions. But outside, you had something that CFD would not do so well at, such as a vapor compression cycle with evaporators and condensers and receivers and so forth, or even just a large extended pneumatic system that probably would not be amenable to CFD analysis. So that's a fairly commonly requested one, but there's other times when you'd want to go between 1D and 3D flows, such as custom piping components or intakes and vents in a cabin or vessel. The idea being a cabin or vessel might be CFD, but all the rest of the systems are more amenable to 1D flow. Or that heat exchanger example I gave earlier, where CFD solves a unit cell, and then TD FlowCAD takes over at the system level when you have 10 million of those unit cells in your heat exchanger. So in terms of closing remarks, as you probably saw here, there's a lot of possible applications here. There's a lot of things we could be doing with this setup, and we're looking for feedback on that. If you have an application you'd like to talk to us about that, or if you have suggestions for future releases. Basically, this is new and different, and therefore that's your chance to kind of influence where things are heading and hopefully benefit from it downstream when the new features come out. Put your fingerprints on it, in a nutshell. We definitely would prefer to not be building in a vacuum here and doing what we think is needed. We'd rather have people tell us what they would like, and we see how we can accommodate it. So with that, I will close out the lecture part of this and switch over into answering some of the questions that have been listed here. You feel free to add more, or if there's ones you don't want to discuss in front of everyone else, please write to support and talk to us about it. Okay, so one question is, can it handle finite difference surfaces or just finite element surfaces? So that's an astute observation. Yeah, it pretty much just handles finite element. In other words, we're relying on system coupling, and system coupling doesn't speak finite elements, it speaks only finite differences. So you have to have a finite difference surface. And I guess I should go back to this example. This looked kind of finite difference-like, but it's not. It was a finite element model. And so, yeah, in order to provide that coupling and all the shape factors and so forth that are required for mapping, it does need to be finite element. And again, we're hoping that people start in space claim and either go into Fluent from there, or TD Direct, or both. And then that's a pretty natural connection. Another question is, will CRTech provide user support for Fluent? Well, Fluent is not our product. We don't sell or support it. So the answer is no, but yes, because we do have it. We do have the ability to run it. And the purpose of that is to be able to do user support for people who are solving coupled problems. So in other words, we can help you with the coupling. We won't be able to answer your questions about what you should do inside of your the Fluent side of your model. There's a lot of good material from ANSYS, self-paced training and videos and classes available there for learning that. But if you do have a problem with your Fluent model, you'll have to ask ANSYS about that. We will help with the coupling, or of course the TD side. Another question is, can you work with other CFD codes? Well, right now we're using system coupling to achieve a lot of this. But if you've been watching what we're doing in the last few years, you've seen that there's been a big push towards APIs and connections with other software and co-simulations, and that's not going away. So right now, the low-hanging fruit is ANSYS tools, but some of the things like you saw go by there, like OpenSF, that's actually kind of a subset of OpenTD, which is the API inside of Thermal Desktop. And that API allows you to do a lot of things, but one of the things you can do is to drive or communicate with other tools. In order to do co-simulation, you just don't communicate with Fluent or with Thermal Desktop. You also have to communicate with Fluent. So I guess it's a long way of saying that the answer is no right now. We can't handle any other codes besides Fluent and pretty soon CFX. But we're hooking up with a lot of codes. I shouldn't use that term. We're hooking up with a lot of other codes these days, and for co-simulations. So chances are, you know, if there's a good API and of course there's enough demand and the cost isn't too high of doing it, and we certainly would welcome you to, you know, just ask first of all, hey, can you work with this code? If not, why not? When? Here's what it would take, and maybe even participate if we fall below the limits of our cost benefit on doing that kind of connection. Let's see, another question is, can you use FlowCAD to model a fuel system, but CFX to model the pump? Yeah, well, first of all, I guess the answer is no right now, no, but that's a little bit of where we're heading. If you look at the idea of the 1D flow connections, of course, that would be right now to Fluent, but eventually, hopefully, to CFX also. That would be a prerequisite to being able to say yes to your question. Of course, the other prerequisite is the CFX itself would have to come online in enough ways in system coupling. Probably, again, it'll follow the path of Fluent of connecting first to surfaces and then the flow connection. That's something we're working on with ANSYS. It's not really available to the public, so that would have to come later. But eventually, I'm sure they'll get there. But I also kind of wonder, to answer your question, you know, if using CFX to model the pump, it's kind of tough to combine a analysis like that into a what if you're going 3,000 RPM and for 5 hours sort of analysis. So in other words, you know, some of that doesn't transcribe itself into, can I treat the pump as, you know, quasi steady for a system level analysis? And you may have to go into producing, you know, performance maps to do that coupling. So how's that for an answer? You get 3 parts, 2 are soon, and the third is that's a tough one. Let's see. Is this integrated within Workbench? Well, that's a good question. You know, system coupling is in Workbench and Fluent's in Workbench, but we haven't actually done much work about testing this out within Workbench itself. It just seems like a lot of the Fluent users are not using Workbench. They're working on the side versions. But yeah, if people come to us with that, we'll definitely look into that, and it should be doable, but we definitely have not done it yet. Okay, here's another question. Can I use Fluent VOF for a tank, but TD for walls and insulation? Well, I guess the knee-jerk answer is yes, because using system coupling, we don't know or care what's happening inside your Fluent model or what methods you're using. So if you're using the VOF or volume of fluid method, then yeah, you can hook them together. But I guess I kind of have to wonder about the application for doing that, because you know, if you're using VOF, you're probably interested in longer time scales, thermal time scales, and I don't think VOF can solve in steady, but I'm not, you know, a Fluent expert. So that there again might be a collision of application rather than, yes, you can do it as a capability, but maybe you don't want to. I don't really know. The question is kind of aimed, I think, towards applications like stratified tanks. And that's definitely still a no man's land where we're trying to come up with tools that transcend what TD-FlowCAD can do and maybe exploit some of what CFD codes can do. But there's no end product to that yet that we can point to. Lots of people are working on that same problem if that was the genesis of the question. And if not, maybe you can write to us on the side and we'll take a look at that. And I'm not seeing any other questions coming in. So I thank you for your time. I hope this has been a benefit. And again, I hope that you have a chance to look over your applications, think about them, and maybe get back to us about which one you'd like to try first, or which one, if we can't do it, you would like us to be heading toward. Appreciate your time. Thank you.